Hi everyone. So in this video, we're going to be talking about some applications of trigonometric functions. Specifically, we're going to be focusing on something that is called simple harmonic motion. So we'll get to what that is a little later, but I want to start by just sort of talking generally about why is it that we can use trigonometric functions to model a lot of situations in the real world. Like, what is it about trigonometric functions that makes them well suited to modeling different situations? So there's really two kind of properties of trig functions that I want to talk about. The first is that they are periodic. So remember that a periodic function is a function that repeats itself with a particular pattern over and over. So here it says trig functions are periodic, meaning that they repeat their pattern over and over. So what else is kind of special about trigonometric functions? Well, trig functions, and specifically in this case talking about sine and cosine, and we'll see that that is going to be the focus of this video, the functions sine and cosine are waves, right? They have this shape where they go up gradually, they reach their maximum, then they go back down to their minimum, then they go back up, right? They have this kind of wave-like shape. So trig functions are waves, meaning that they oscillate. So oscillate is basically just a word to mean that, when something kind of goes back and forth between a highest and lowest value. So they oscillate between a maximum and minimum value. So if you think about it, there's a lot of things in the real world that have these kind of properties, right? That have like a pattern to them, that keep repeating over and over, or that have this kind of wave-like shape, right? That sort of go up to a highest value and back down to a lowest value, and over and over again repeat that kind of oscillation. So just to give a few examples of situations that could be described as wave-like and periodic, one would be the height of the sun. Let me make this a little less bold. The height of the sun in the sky, right? It goes up and then it goes down and then it goes back up again and it goes back down again, it goes back up as the days go by. Another similar example would be ocean tides, right? The ocean, the tide comes in, gets higher and higher, then it slowly goes out, gets lower and lower until it's at its minimum, comes back in, gets higher and higher, goes back out. It has this kind of oscillation that keeps repeating. Another example is animal populations. So certain animal populations will kind of increase until they reach sort of an oversaturation of having, too much of that population. And then, some of the population will start to die off because there's not enough food for them. And gradually that population will decrease. Once it's decreased enough, then there is sufficient food for the whole population and it will start to go up again. So the next two examples I'm going to write down are ones that we actually will focus on in the video. These ones, the first three I wrote down, we're not going to go over examples with those because they're a little bit more complicated. But a very simple example that we will be looking at in this video is a spring moving up and down. So I'm going to show you a video in a moment that really shows what this looks like. But if you picture that you have a spring and it has some kind of a weight at the end, if you pull the spring down and then let go, the spring will kind of bounce down and up and down and up and down and up, right? And so that is this kind of oscillation that repeats. And we'll see that can be modeled very well using sine and cosine. One last example that we'll also see in this video is when sound is produced. So how does sound work? I'm not an expert on this, but roughly speaking, sound has to do with air pressure varying, right? So like when a sound happens, you're kind of vibrating the air and that will cause it to compress and then it will decompress and it creates these waves. You might have heard of sound waves. So that's another example we'll look at in this video. So air pressure variation when sound is produced. So this is just a very small sampling. There are a lot of different other situations that can be modeled with trig functions, but hopefully this gives you an idea that there's a reason that we're learning about these functions, right? They are really important. If you take any kind of a physics class, you will see a lot of stuff with trigonometric functions just because they are so good at describing a lot of different phenomena in our world. So as I mentioned, we're going to be focusing on something in this video called simple harmonic motion. So some phenomena in the world can be modeled by combinations of trig functions. So for example, taking the product of sine times cosine or something like that, or even combining trig functions with other types of functions like exponential functions or polynomials. So in this video, we're going to be focusing specifically on phenomena that can be modeled by functions of the form f of t is equal to sine of wt, or g of t is equal to a times cosine of wt. So these would be the two kind of formats that are written down here. These are very simple transformations of sine and cosine, right? That's something we learned about earlier in the quarter, is that we can take our graphs of sine and cosine and we can do different transformations to them. And so these are just very simple, right? This is just the whatever number a is here. This is going to be some kind of a vertical stretch and potentially also a vertical reflection. And then whatever number is in here, that is then going to be a horizontal stretch or compression. So really just kind of taking the basic sine graphs and just stretching them or compressing them in different directions. That's what we're going to be focusing on in this video. I do want to just briefly show you on Desmos what I mean when I say kind of combinations of trig functions or trig functions and other functions. So let me just give you a quick visual on that. So for example, if I take sine of x and multiply that with cosine of 2x, that would give me a graph that looks like this. So we can see that it has, it repeats itself, it is periodic, it has these waves, but the waves are a little bit different from the conventional sine and cosine. And maybe actually let me just pull those up first to just kind of really have those as our base, right? So sine and cosine, those have this kind of smooth wave that just goes up, goes down, goes back up, goes back down. So as I said, these are the kind of shapes we're going to be focusing on in this video, are these very simple, straightforward, goes up, goes back down, goes up, goes back down. But what we're not going to be looking at in this video, but what I think is worth kind of just quickly glancing at, is things like this, sine of x times cosine of 2x. So there are things in the world that can be modeled by situations like this, something that goes up, goes down, goes up, then goes like further up. It doesn't have this exact kind of oscillation that we see with the standard sine and cosine graphs. Another example would be sine squared of x times cosine of 5x. So again, we see this kind of, we see these rising and falling, but it's not doing it with exactly the same pattern that a typical sine and cosine graph would do it with. Maybe let me make this a little bolder. And I would encourage you, by the way, go into Desmos and play around with this. I think it's really interesting to see what kind of shapes you can come up with. What I would recommend doing to get the most interesting shapes is making your inputs different. So for example, notice I did sine of x times cosine of 2x, or sine squared of x times cosine of 5x. That's going to give you more kind of interesting shapes if you change what the inputs are of the two functions. Just to give another few examples, so we won't really be looking at much of tangent in this video, but I just want to quickly show you that we can also kind of change what the tangent graph looks like by multiplying it with something. So this is the graph of x times tangent of x. So that looks pretty different from standard tangent, right? Maybe I'll just remind you so that's what tangent looks like. And if we make it x times tangent of x, it changes to looking like this. Last couple examples I want to show you, these are ones that we're actually going to be looking at in this video. So if you take sine of x and multiply it with an exponential function, so e to the negative x times sine of x, what that's going to do, and I'll zoom in a little bit, is it's going to kind of still have the same waves as sine of x does, but notice how the waves like really flatten out as you get further along on the x-axis. So this is something we'll see just briefly at the end of this video. This is called dampened harmonic motion. And then I also have here we can compare cosine of x with e to the x times cosine of x. So it's kind of the opposite shape, where in this case, it's getting kind of flattened out on the left, and on the right, we're having these really big, tall waves. So again, this is just to give you kind of a taste of what are the different shapes you can produce by combining different trig functions and even trig functions with other kinds of functions. And you can get all sorts of different wave shapes that could be used to model different situations. But yeah, so let's now get into talking about exactly what simple harmonic motion means and looking at some examples of that. So simple harmonic motion, as I mentioned, so this is situations that can be modeled by these very simple transformations of sine or cosine. So situations that can be modeled by functions of the form f of t is equal to a times sine of wt, or g of t is equal to a times cosine of wt. Any situation that can be modeled by an equation of that form is called simple harmonic motion. So I want to define a few terms here, and a few of these we've actually already learned, right? Amplitude and period, we already talked about those when we, back when we first started talking about trig functions, and then frequency will be a new word. So I want to start by just writing down how you kind of can calculate each of these things based on the equation, and then later we'll come back and explain kind of what these things mean in the context of actually modeling a real world situation. So for example, how would you find the amplitude of a trigonometric function that's a times sine of wt or a times cosine of wt? Well, it's going to be the absolute value of this number a, right? So this is something that we learned back when we were talking about transformations. Because this number a is going to be your vertical stretch or compression, and it could be negative, right? That would be also reflecting your graph. But regardless of whether it's positive or negative, that's going to tell you how much your graph is stretched or compressed vertically. And remember that amplitude is like half the total height of your graph. And so it's that vertical stretch that is going to impact that height. So you find the amplitude by doing the absolute value of that number a. Okay, what about the period? So that is something else that we already talked about in the past. If you recall, the period, that is going to be kind of influenced by the horizontal stretch or compression. And the horizontal stretch or compression, that comes from the number that's getting multiplied with t. And so specifically, if you take 2 pi, which is kind of the standard period, and you divide it by whatever number t is getting multiplied with, that is going to tell you your period. So in this case, it's 2 pi over w. Okay, so finally, there's something called frequency. And so frequency, we'll come back and talk about exactly what that means in a little bit, but I'm just going to tell you for now how you calculate it. So to find the frequency, you do the reciprocal of finding the period. So you do whatever this coefficient is, w, you divide that by 2 pi. And again, after we look at an example, I think once we see an example, it'll be a lot easier to understand exactly like what the significance is of things like period and frequency. So we'll come back to that. Okay, so let's look at an example of, as I mentioned, a mass suspended on a spring. So I want to quickly show you a brief video that can show why is it that trig functions are kind of the appropriate thing to model this type of situation. So in this video, we're going to see maybe I'll play it and then pause it when we get to them actually showing it. So what's going on here is we have a spring. It's kind of hard to see. It goes kind of all the way up to the top, and then it's attached to this spray paint can. And so the spray paint can is serving the purpose of being kind of a weight at the bottom of the spring. And then additionally, it has the purpose that because it's a spray paint can, it can actually be used to record its position. And so what's going to happen is they're going to allow the spray paint can to kind of bounce up and down, and then they're going to scroll this paper along to kind of represent the passage of time. And we'll see that when the spray paint can bounces up and down and the paper kind of moves to the side, we'll see that it actually forms something that very convincingly looks like a sine or cosine wave. So press play. And by the way, I'll put a link to this video and a few other videos that we'll see in the description of the video you're watching right now. Yeah, we can see that that looks like a sine or cosine graph, right? And so that's why when we're talking about springs bouncing up and down, that simple harmonic motion, these simple transformations of sine and cosine are an appropriate thing to really measure them. And again, because the paper being moved, you can think of that as representing the passage of time, right? So as time goes on, the paint can goes up and down, and it kind of repeats that pattern of going up and down, forming these waves. Okay, so in this case, we're given the equation, and actually there's one other thing I need to define here. So there's this word displacement. So displacement is a word that if you take a physics class, you'll definitely see, and you'll definitely see it in calculus. Displacement is basically the same as distance, except that it can be positive or negative, right? When we're talking about a distance, you're generally just talking about positive. You don't say, oh, my friend lives -2 miles away from me, right? You just say 2 miles. So with displacement, we're kind of keeping track of direction. And so when something moves in one direction, it's counted as positive, and if it moves in the other direction, it's counted as negative. So displacement is like distance, but counted as positive or negative depending on direction. And so in the case of what we'll be looking at here with this spring, basically when it's at its kind of resting position, that's considered 0. When it bounces down below that resting position, that is considered negative displacement. And when it goes up, compresses up above its resting position, that is considered positive. So it's basically just displacement. You can kind of think of it as like position, where position, there's some position that's considered 0, and above that position is considered positive, and below that position is considered negative. Okay, so we're given this equation to represent the displacement of this mass on the spring. And first thing we're asked to do is find the amplitude, period, and frequency, and we want to explain the significance of each. Okay, so how do we find amplitude? Well, amplitude, remember, was the absolute value of the number that is getting multiplied with our sine function in this case. So it would be the absolute value of 10, which is just 10. So that is our amplitude. So what is the significance of the amplitude in the context of this problem? Like what does the amplitude tell you about this situation? And actually, sorry, I'm gonna take that back. Let's return to this significance question after we look at the graph, because I think once we look at the graph, that will kind of clear up what the significance is. So let's just go through and find the amplitude, period, and frequency. And once we have those, and we look at the graph, then we can kind of make the connection of like what each of those signifies. Okay, what about the period? Well, remember that we find the period by taking 2 pi and dividing it by the number that's getting multiplied with t. So in this case, that would be 2 pi divided by 4 pi. So that would simplify, the pi's will cancel out. We'll have 2 over 4, which is 1/2. And then finally, we have the frequency. So that's the new term. And the frequency is just the reciprocal of the period. So, I mean, we can just immediately say that it's 2 over 1, but really the way we calculate it is by doing the opposite. We do the coefficient of t divided by 2 pi. And so in this case, that would simplify to 2. Okay, so let's take a look at the graph of this function on Desmos. We could graph it by hand, right? Like we know how to graph something. If you know its period and its amplitude, we do know how to graph it, but some of these get a little bit complicated and the numbers are a little annoying. So I think it's probably best that we just look at the graphs on Desmos. So this is what the graph looks like. So we can see that the amplitude is 10, right? So the amplitude is supposed to be half of the total height. So it goes from the midline being 0 up to a maximum height of 10 down to a minimum height of -10. That's why the amplitude is 10. So what does that tell us about the significance of the amplitude? Like, what does the amplitude tell us about this situation? Well, it basically tells us how far this object travels in each direction from its kind of midline, right? It goes up by 10 and it also goes down by 10. So maybe let's just add that here too. So this is basically the distance traveled by the spring, or really by the mass at the bottom of the spring. So I'll just say by the mass in each direction. That's the significance of this amplitude. Okay, so now let's look at the period. So the period is supposed to be 1/2. We can verify that here. So remember, the period is how long it takes to go through one cycle. So here's the start of the cycle. It goes up, it goes down, it comes back up, and we can see that that cycle ends at 0.5. So that is a period of 1/2. So what does that represent in terms of this word problem? If we're imagining the spring kind of bouncing up and down and up and down, what is the significance of the period? Well, that's the amount of time that it takes for this object to go through a full cycle, right? To go up all the way, down all the way, and back to its kind of starting point. So the period is the amount of time, I don't know what is going on with my pen, amount of time to complete a full cycle. And then finally, frequency. So what is going to be the meaning of this frequency? Well, here the frequency is 2. So let's think about what that number 2 tells us. So because the period is 1/2, how many cycles does this graph go through in 1 second? Well, it goes through 2. Right? Because the period is 1/2, how many of those 1/2s do we fit into 1 second? We fit in 2, right? It goes up and down and back, so that's one cycle. Then it goes up and down and back, and that's another cycle. And so what does the frequency tell us? It tells us the number of cycles per time unit. And so in this case, the time units we're working with are seconds. And so the frequency means the number of cycles per second. So this is the number of cycles per second. And I guess, here I put, the units are, so centimeters are the displacement units and seconds are the time units. And maybe just say one more thing. So talking about displacement, again, just to kind of remind you what displacement means. Remember, displacement is like distance, but with direction. So now that we have the graph, I think we can see that a little bit better. The displacement is +10 when the spring is at its kind of most compressed, most like up position. And it's considered to be -10 when it's all the way down at the furthest it gets below its resting position. So 0 is like kind of the just resting position. Going vertically up of that is considered positive displacement, and going down compared to that is considered negative displacement. So I want to just now take what we figured out here and kind of write it in general as a general rule for amplitude, period, and frequency. So what does amplitude tell us in general? It tells us the maximum distance traveled. And we'll see that in some cases, we're not going to be talking about distance. So the word distance isn't always the appropriate thing, but I think it's an okay way to kind of think about amplitude. It's the maximum distance traveled in each direction. So not like the total distance traveled from the very top to the very bottom, but if you just kind of think from the middle, what's the furthest it goes in each direction, that's your amplitude. The period is always going to be the amount of time to complete one cycle, whatever that means in the context of the problem you're looking at. And then frequency is always going to be the number of cycles per time unit. And that's really just because it's the reciprocal of the period. So if you know how much time it takes to complete a cycle, if you do 1 divided by that, that will tell you how many cycles occur per that 1 time unit. And doing 1 divided by a number is the same as taking its reciprocal. So that's really why that works the way it does. Okay, so we looked at the graph on Desmos. Now I want to answer one last question. So this is something that, that relates to actually the last 2 videos that you should have watched. So this says, at what times is the spring at a height of 5 centimeters? Find the first 4 times. So what do we need to do in order to solve or to answer this question? Well, this is telling us that the spring is at a height of 5 centimeters, and it's asking us to find a time. So remember how this function works? The output is centimeters, right? And the input is seconds. So if they're telling us that the output, that the height is 5 centimeters, that means that we want to set our function equal to 5 and solve for time, right? They gave us the output and we're trying to find the input. So we want to set 5 equal to our function, which is 10 times sine of 4 pi t. And we want to solve this for t. So how do we start by solve this for t? Well, we can divide both sides by 10 to start with. So we have 5 over 10 is equal to sine of 4 pi t. And then 5 over 10, that reduces to 1/2. So 1/2 is equal to sine of 4 pi t. Okay, so how do we go from here? Well, I would encourage you to pause this and try it yourself because, like I said, this is something very, very similar to what we did in the last couple videos, or in the last video, which is solving a trig equation where the input is not just t or x. It has a different period. So pause this and try it yourself. But yeah, what would we do here? Well, we can replace where it says 4 pi t, we can just replace that with a different letter and kind of solve it as a normal trig equation and then see what adjustments we need to make at the end. So typically people will use the letter u or w. Let's use u because w is already kind of has another meaning in these problems. Okay, so 1/2 is equal to sine of u. So we want to figure out what are the angles that would make this true. What are the angles where sine of that angle is equal to 1/2? Well, one angle that would work would be pi over 6, right? If you go to an angle of pi over 6, you have an x coordinate of square root of 3 over 2 and a y coordinate of 1/2. And so therefore, sine of pi over 6 is equal to 1/2. So you could equal pi over 6. That's one possibility. What's the other possibility, kind of looking at the unit circle? Well, the other possibility would be 5 pi over 6, right? If you go to an angle of 5 pi over 6, now you have an x coordinate of negative square root of 3 over 2, and then the y coordinate, which is what we want here because we're talking about sine, is still 1/2. So that tells us that u could also be 5 pi over 6. Okay, so how do we go from here? Well, remember that that's not really the equation we were trying to solve. We were trying to solve sine of 4 pi t is equal to 1/2. And so what we need to do now is instead of writing u is equal to pi over 6 and 5 pi over 6, we now just need to replace that with 4 pi t. So 4 pi t is equal to pi over 6, and 4 pi t is equal to 5 pi over 6. And so if we solve each of these, that will tell us what actually, the actual solution, what t would need to be. So both of these have a pi, so we can divide both sides by pi. And then on this first equation, we can divide both sides by 4, or maybe you can think of it as multiplying both sides by 1/4. Maybe I'll rewrite this. So this is what we have right now, right? 4t is equal to 1/6. If we multiply both sides by 1/4, we would get t is equal to 1 over 24. And then on the other side, similarly, we have 4t is equal to 5 over 6. If we multiply both sides by 1/4, we get t is equal to 5 over 24. Okay, so those are two of our solutions. Let's see what this problem is actually asking. This is saying find the first 4 times. So we just found the first 2 times. How do we find more times? Well, we add the period, right? This is this idea we've seen quite a bit when we're talking about solving equations with trig. Once you have your first 2 solutions, you can find more solutions by just adding that period to each of them. So we do have to be careful because in this case, the period is not 2 pi, right? We know that the period, we found that earlier, the period is 1/2. And so to find our next 2 times, that would be solutions, we want to add 1/2 to each of these. So that would give us t is equal to 1/24 plus 1/2, and t is equal to 5/24 plus 1/2. And so we just want to make a common denominator, and that will give us our final answer. So for this one, if we multiply the second fraction by 12/12, we would get t is equal to 1/24 plus 12/24. So that would be equal to, sorry, my screen is a little stuck, 13/24. And then similarly here, we would have t, if we multiply this one by 12/12, we'd have t is equal to 5/24 plus 12/24. So that would be 17/24. And maybe I'll make a note for people who are just looking at the lecture notes. So this is the period, right? That's why we're adding this number. Okay, so what is our final answer? What are our first 4 times? Well, we found t is equal to 1/24, 5/24, 13/24, and 17/24 seconds. And we can check this by looking at the graph. So if we look at y is equal to 5, right, we're looking for where is the height equal to 5. If we look at these first 4 solutions, maybe I'll just select these first 2. These are the decimal forms of 1/24 and 5/24. And then if you take 1/2 and add it to each of those, that will give you those 2 solutions. And if you wanted to find even more solutions, you could just keep adding 1/2, and that would give you all these other solutions that we see. All right, so let's look at another example. Okay, so this example says sound is produced by a regular variation in air pressure. If the pressure varies in simple harmonic motion, then a pure sound is produced. So I'm going to show you some visuals to kind of help you understand what's going on here. But yeah, so in these cases, if we're looking at sound, and you may have seen these kind of sound wave pictures, right? Like machines, and again, I'll show you a video of this in a moment, but there's these machines that can actually show you what the sound waves look like as you're talking or playing music or whatever it is. So what does the frequency tell us? The frequency tells you the pitch of your sound. So basically, how high or low the sound is. So if you change the frequency, if you make your voice get higher, playing an instrument, you're playing a higher note or a lower note, that will change the frequency. It'll make the waves of the sound actually be a different shape. So what about the amplitude? The amplitude is going to tell you the loudness. So if you have like the same kind of wave shape, but then you get louder, that will not change the frequency. The waves will still kind of repeat in the same pattern, the same amount of time, but they'll get taller. As it gets taller without changing the pitch, that will cause it to be louder. So let me show you a quick visual of this. So maybe I'll show you this first. So this one is just an example of someone kind of talking or just making kind of weird noises, and you'll see that the waves that are produced are not kind of perfect sine and cosine waves. And I guess I don't know if you're going to be able to hear this, which is unfortunate. So I'll link this. You should definitely watch this video and the next one I'm going to show you on your own so that you can hear the sound, because I'm not sure it's going to come through in this video. but yeah, so this is someone just kind of going, or like making noises. It's not a pure sound, so we're not seeing perfect sine and cosine waves. This one I'm going to show you here, now it's going to be like a machine just making kind of a tone. And what's going to happen is, so we see this kind of sine wave, right? And right now what's going on is the sound is getting louder and louder without changing the pitch. And we can see that the amplitude is changing, right? The period and the frequency, those are not changing. And now the sound is actually getting lower. And so as the pitch gets lower, notice that the frequency decreases. The period gets longer, and now it's getting quieter again on that same pitch, and then now it's silent. So I'll link that because you should really, really watch that with the sound so you can really see what I'm saying, that the pitch is going to change the frequency, whereas the loudness is going to change the amplitude. And so that machine, by the way, that's basically just kind of measuring or giving a visual for what's happening in the air. So what's happening in the air is that the air is vibrating, and so its pressure is changing in this kind of wave-like shape. And so when we're talking about sound waves, that's really what we're talking about, is how is this air pressure varying? Okay, so the actual problem we're focusing on says a sousaphone player is playing the note E. The variation in air pressure is given by the following function. And the units, by the way, are for the output are pounds per square inch. So that's a pressure unit, right? And then the input unit is seconds. And again, without sound, I'm not sure how interesting this will be to you, but I will link this below if you're curious what a sousaphone looks like or sounds like. This is an example. This is actually a pretty impressive video of these people all playing together. So I'll link this so you can check it out with sound, because it's cool. I didn't know what a sousaphone was before watching this video, and now I do. Okay, so first thing we want to do is we want to find the amplitude, period, and frequency of this, in this situation. So again, the way we find the amplitude is the absolute value of the coefficient. So in this case, the absolute value of 0.2, and the absolute value of 0.2 is just 0.2. What about the period? Well, the period, again, that is going to be the 2 pi divided by the coefficient of t. So 2 pi over 80 pi. And so that reduces to, the pi's cancel out, right? And then we have 2 over 80, which is 1 over 40. So that is the length of one cycle. And the units for that would be seconds, right? So a cycle is completed in 1/40th of a second. So when we're talking about music, unless the note is like very, very, very low, the waves are going to happen very quickly. And so then we also have the frequency. So remember, the frequency is the reciprocal of the period. So we would do instead 80 pi over 2 pi. And so in that case, we get 40. And so that tells us that we're going to have 40 waves per second happening in this. And I can even write that down, waves. Or maybe waves is not the right word. I'll say cycles per second. And I have the graph of this one pulled up, so maybe I'll grab that now. Here we go. So we can see that, so here's the start of a cycle. The cycle ends at 0.025, so that is 1/40th of a second. And we can't even see it all here, but if you keep scrolling over, we could get to 1 second. So 1 second is here. So between 0 and 1 second, 40 cycles have happened. So very, very fast waves happening. And by the way, when we found the frequency, this actually is like the frequency for an E note. It's going to change based on what octave you're in, but at least for whatever E this is the frequency. And that same frequency on any instrument should still produce the note E. That's, again, not something I'm an expert about, so I don't want to talk about it too much, but it's definitely true that frequency is really what like determines what pitch your music is going to be, like what note it's going to come out as. All right, next question. If the player starts playing louder, what will change? So this is something we talked about earlier, which is what is it that affects the loudness? That is the amplitude, right? So the amplitude will increase, but the frequency won't change unless they change their note. So louder sound just means bigger waves in terms of their tallness. So next question says, if the instrument is a little bit flat or a little bit out of tune and the E is playing a little bit flat, how will that change? Like, how would that compare to this kind of nice equation we were given? So what does it mean for a note to be a little flat? It means it's a little lower than it should be. So what happens, what is it that is going to affect the pitch of our music? That is the frequency, right? And the frequency is related also to the period. And so in order for the note to be lower, that means that the frequency would be decreasing. So the frequency will decrease. The higher the frequency, the faster those waves are occurring, the higher the note. So if the note is a little bit lower than it should be, that means that frequency is going to be going down. And frequency decreasing is the same as having a longer period, right? Because the longer it takes to go through a cycle, the fewer cycles will happen per time unit. All right, last question, kind of similar to the last question we did on the last one, is at what times is the air at its normal pressure? Find the first 4 times. So I guess normal pressure maybe is a little bit ambiguous, but if we're thinking about sound as kind of changing the air pressure, right? It's compressing and then it's kind of in response like loosening and then compressing and loosening. Normal means kind of that middle midline, right? So we think of these waves as compressing and then stretching out. We're looking for when are we at that middle value. And so what is that middle value going to be? Well, that's going to be 0, right? So 0 is like the midline of our function. So we're always going, it's like with the spring, right? The spring goes up and it goes back down and it goes back up and it goes. So the kind of midline of 0 is sort of the resting point. That's like the natural point when there is no compression or stretching. Same idea here. So when we compress, that's going to end up being this positive number, and when we stretch, it's going to be a negative number. Normal is going to be considered 0. So this is 0, and I think what were the units? These were, I forget, let me write that down, pounds per square inch. So similar to what we did on the other one, we're given the output, and we want to set that equal to our function to find where, at what times we reach that output, right? And so we're going to set 0 equal to our function, which was 0.2 sine of 80 pi t. Okay, so we can divide both sides by 0.2, right? And that won't affect the left-hand side. So we have 0 is equal to sine of 80 pi t. And at this point, I would encourage you to pause the video and try this yourself because this is very similar to the last one we did. So if you remember what we did in the other one, we, instead of saying just sine of 80 pi t, we used another letter as kind of a shortcut, something to represent 80 pi t to make our equation easier to solve. And then at the end, we went in and we put that 80 pi t back in. So this is asking us, at what angles is sine equal to 0? So where is sine going to be equal to 0? Well, it's going to be at 0, right? That is one angle that is going to work. That's like the first angle that's going to work. So this would be where the y coordinate is 0. And then the other angle that's going to work is the angle of pi, right? At pi, we also have a y coordinate of 0. And so that means us that we could have u is equal to 0, or we could have u is equal to pi. Okay, so how do we go from here? Well, we're not trying to solve for u, we're trying to solve for t, right? So we need to go back in and replace u with 80 pi t. So 80 pi t is equal to 0, and 80 pi t is equal to pi. And so for this first one, we can divide both sides by 80 pi and the right-hand side still stays 0. So this one actually, u being 0 is equivalent to t equaling 0 in this case. In this one though, if we divide both sides by pi, then we have 80t is equal to 1. And then we divide both sides by 80 and we get t is equal to 1 over 80. So those are the first 2 times that we reach this air pressure, this kind of midline air pressure of 0. We want to find the first 4 times. So again, we need to add the period. So what is the period in this case? Well, that was 1 over 40, right? So we're just going to take each of these fractions and add 1 over 40. Okay, so for the first one, that is pretty simple. That just gives us 1 over 40. And then for the second one, if we make a common denominator, that is going to give us 1 over 80 plus 2 over 80. So that is going to be 3 over 80. And I'll make a note again for the lecture notes. Again, this is the period. That's why that number is getting added on. And so now we have our 4 times, right? We have t is equal to 0. We have t is equal to 1 over 80. We have t is equal to 1 over 40. And I guess I didn't have to keep writing t is equal to, but that's okay. And t is equal to 3 over 80. And the units on all of these are seconds. And again, we can confirm this by looking at our graph. So if we go back to the graph, we're looking for the places where we're at 0. Let me go back to here. So that would be here, 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 and here. Those are our first 4 times. And so the first 2, 0 and 0.025, those were the first 2 we found. And then the next 2 are achieved by adding the period of 1 over 40 to each of those. Okay, next example. Actually, sorry, I think I had one other example. Yes, this one. Let's do this one first, and then we'll talk about one last thing, and then we'll be done with this video. So the last example I want to do in terms of simple harmonic motion, we now are going to write the equation ourselves, right? In the last couple, we were given the equation, and from that we found the period and all those different features. In this case, we're actually given the information we need and we have to actually write the equation. So this is another spring example. So the spring is compressed and then released and it kind of goes up and down. And it tells us that it is compressed by 4 centimeters. And it says that the mass returns to its compressed position after 1/3 of a second. So the first thing we want to do is we just want to identify what the amplitude and the period are. So by finding the amplitude and the period, that's going to be enough for us to actually come up with our equation. Because remember, the amplitude, that impacts that coefficient that's in the front of the whole function. The period is going to impact the coefficient of t. And so really those 2 things will be enough. The last piece will be figuring out whether we want to use sine or cosine, and we'll talk a little bit more about that in a moment. But okay, let's think about what the amplitude is. So it says the spring is compressed by 4 centimeters. So picture that the spring is at kind of its resting position, and then you kind of push it up by 4 centimeters. So that is going to be the maximum kind of height of this thing, right? If it starts at its resting position and you compress it by 4 centimeters, that's going to tell us the amplitude, right? That's going to tell us how high, like the difference between the resting position and the highest position. And based on what we've seen about what these graphs look like, we know it's actually going to go then down by 4 centimeters. The amount that it is compressed is going to be actually the same amount that it kind of stretches in the other direction. So the amplitude is going to be 4. Hopefully that makes sense. So again, amplitude is just like the furthest distance that your object travels compared to its kind of resting position. And because it's been compressed by 4 centimeters, that tells us that that is the distance. That's as far as it's going to get from its starting point. Okay, what about the period? So that one is actually kind of handed to us. It says that the mass returns to a compressed position after 1/3 of a second. So just kind of picturing what this graph might look like, if here's our midline of 0, and the graph starts up at its compressed position. Maybe I'll even kind of draw some axes here. So, this is 4 centimeters. This is -4 centimeters. So what this problem is telling us is that we're starting at this compressed position of 4 centimeters. If we think about this as being, a trig function, it's going to be going down to its minimum, then it's going to come back up. And so what this part of the problem is telling us is that the amount of time for it to kind of go all the way down and come all the way back up to its compressed position, it's telling us that that is a time of 1/3 of a second. So this is 1/3 of a second. So what is the period of this function? Well, it's 1/3 of a second, right? Like the period by definition is the amount of time it takes for the function to go through its cycle. And if this is telling us that it's compressed, released, it goes down, it comes back up to its compressed position after 1/3 of a second, well, that's the period. Okay, so the other thing we can figure out based on this kind of rough sketch that I made is whether it makes more sense to use a sine or a cosine graph. So this looks more like a cosine graph, right? And so where did I come up with this? Like, why did it end up looking like a cosine graph? Well, it's because the problem told us that it was started by being compressed, right? The clock is starting at the time when the graph is, or when the spring is compressed. And so that means that it's starting in its maximum position and going down from there. And so which of the trig functions starts at its maximum and then goes down, that would be a cosine graph. Okay, so now we know we're working with cosine and we have the amplitude and the period, we know that our function is going to look roughly like this, a times cosine of wt. And so the only question now is what is going to be a and what is going to be w. So a is going to be equal to 4, right? Because that is what tells us the amplitude. The graph is not reflected, it's not upside down, so it's going to be positive 4. And then how do we find w? Well, basically, we know that the period is going to be 2 pi over w. So to find w, we can say this. We can say 1/3 is equal to 2 pi over w, and we can just solve that for w, right? Because that's a general rule for finding the period, is that the period is supposed to be 2 pi divided by whatever number this is. So in this case, we know the period is 1/3, so we can set up this equation and solve. So if we solve this equation by cross multiplying, we would find right away that w is equal to 6 pi. And so now we can write our final answer, which is that f of t is going to be equal to 4 times cosine of 6 pi t. Okay, last thing I want to show you, and did I do a graph of that one? I'm not sure. Yeah, here we go. This is our graph. We can see that it's starting up at the highest compressed height. It's going back down. It's coming back up. It's going through that cycle in sorry, that's not the full cycle. Here's the full cycle. It's going through its full cycle. It's going all the way down and back up in 1/3 of a second, right? 0.333 is 1/3 of a second. Okay, last example I want to talk about, and this isn't something that you're really going to be responsible for like knowing for a test or quiz or anything, but I just wanted to talk about it because I think it's kind of interesting. So all the examples we've looked at so far are assuming that whatever is going on with this wave is just going to like keep going forever and ever and ever. And realistically, that's not how things work in this world, right? We have things like friction and air resistance and all these little complications that can cause motion to slow down, right? For example, if you're pushing someone on a swing and you let go, it's not going to keep swinging to the same height. It's going to eventually swing less and less and less, right? And you could also picture like with the spring, if you let go of a spring and kind of let it bounce up and down, it's not going to keep bouncing forever and ever and ever, right? It's eventually going to kind of, the bounces will get smaller and smaller. So everything we've talked about so far in this video has really been kind of an idealized version. It hasn't been like super realistic, and that's fine for our purposes. But I did want to mention how we can also model this idea of these waves that are getting smaller and smaller. So examples of this, I mentioned a couple, but one might be a note getting quieter and quieter as time goes on. So like, for example, if you, let's say, pluck a guitar string, it's going to be vibrating, it's going to be producing these sound waves, but it's not going to keep vibrating the same forever, right? It's eventually going to vibrate less and less, and that you'll hear this tone kind of die out. So that's an example of what we're calling dampened harmonic motion, waves that are kind of getting smaller and smaller as time goes on. Another example would be, like I said, a spring. A spring eventually stops bouncing up and down, right? It bounces less and less until it eventually stops. So these types of situations are called dampened harmonic motion. And so they can be modeled with these functions that in some ways look very similar, but there's one really key difference, which is the inclusion of this factor of e to the negative c times t. So what this accomplishes, and we'll look at this in a graph in a moment to kind of give you a visual, but if you think about like what the graph y is equal to e to the negative x looks like, it's a graph that looks kind of like this. It's a graph that just goes down and down and down and flattens out. And so when you have something like this, like e to the negative some number times t, it's going to give you these graphs that go down and down and down as time goes on. And so if you multiply that with a sine or cosine graph, it's going to cause you to have this graph that still has these waves, but the waves are going to be kind of getting smaller and smaller. It's like you're kind of blending together this exponential decay function with a sine or cosine function, giving you a function that kind of has the properties of both of them. Okay, so let's look at a quick example. So it says the G string on a violin is plucked by pulling the string a distance of 5 centimeters above its resting position. Which of the following functions is a better model for the vibration of the spring? So the first one says f of t is equal to 0.5 times cosine of 400 pi t. And so by the way, this number here, 400 pi, that is a result of like knowing the frequency for the note G. So as I mentioned earlier, every note has its own kind of special frequency, and the frequency corresponds to what this number is going to be. So that's not made up. That's why that's 400 pi. So this one, this 0.5, that reflects the fact that the string was originally pulled 5 centimeters away, and then it's going to kind of go back down and go back up and go back down. So this first example would be if the string was showing simple harmonic motion. So simple harmonic motion, meaning that it's just going to continue going up and down with that same pattern forever. If we compare that to this second one, what's the difference with this one? Well, this one has this extra factor of e to the negative 1.4 times t. And as we mentioned, functions like that have this shape where they kind of go down and down and down. So this second example, this is dampened harmonic motion. So this would be a situation where instead of the string going perfectly up and down, vibrating the same amount forever, as time goes on, the string is going to vibrate less and less. The sound is going to kind of die out. So which one of these sounds more kind of realistic for what would happen in the real world? Well, the second one. So the second function, and that's going to be because the string will vibrate less as time goes on and eventually stop vibrating at all. And so I don't know a whole lot about these, so I want to be careful that I don't try to say anything that I'm not sure about. But basically, in a world where maybe there was no air resistance or friction or anything like that, then maybe it would just keep going forever and ever and ever. But there are all these different things in our world that kind of just slow things down. And so that's why this second one is really more realistic for what would happen in the real world. So I'm going to just show you what the graphs of these things look like. So this one that is currently graphed in orange, this is the simple harmonic motion version. So this is where it's just going up and down and up and down forever, same vibration, never slowing down. This is what it looks like with the dampened harmonic motion model. So notice that the waves are still lining up. They're like exactly the same kind of shape, but on the dampened harmonic one, the waves are getting smaller and smaller and smaller as time goes on. And so why is that? Well, again, it's because we're multiplying the simple harmonic motion function with this exponential decay function. So I want to show you what that would look like on its own. So this green function here, this is if you graphed just 0.5 e to the negative 1.4 t, and you can see that kind of traces out where the tops of these are going. And then if you do the negative of that, that also traces out now where the bottoms of these things are going. So basically by multiplying, because usually sine and cosine have a maximum and minimum of 1 and negative 1, if you take 1 and negative 1 and multiply them with this function, that gives you your new maximum and minimum values. And so that's why we have this kind of upper and lower bound. Again, I'm not going to hold you responsible for dampened harmonic motion, but I just wanted to show it to you in case you thought it was interesting and because it is kind of a better representation of what's going on in the real world. All right, that is it for this video. Like I said, please check out the links that I'll put in the description of this video so that you can see some of the other videos that I shared with sound, and I will see you all later.